In this video, I'm going to talk about electric potential and electric potential energy. So let's say this is a universe and these are the points, random points in my universe. Okay. Um, Potential is a number associated with a point in a space. So you can see a lot of points, right? You can plot as many points as you want. Now the potential at this point V equals 0 because we don't have a charge in our universe. Okay, there is no charge in the universe, so the potential at this point is 0 volt. Volt is the unit of potential. What about other points? Yeah, all of them will be 0 because we don't have a charge. V equals 0, V equals 0, V equals 0, V equals 0. I'm going to bring in a charge, a positive charge to my universe. Okay, so I have placed a positive charge here. Let's say 10 coulomb charge. The moment you introduce the charge, the potential values will change. It will be a not zero number. Okay, so this point, let's say 10 volt. These are just random numbers. Okay. Let's say 8 volt. This point, let's say 6 volt. This point, let's say 4 volt. Okay, yeah, this will not be 0. Yeah, so different points will have different potential values. If the points are at the same distance from the charge, they will have the same potential values. This point and this point are almost at the same distance from our main charge. So their potential values will be the same, 10 volt. So 10 volt here, 10 volt here. Yeah. As you go away from the main charge, the potential values would decrease. And if you have a point at the infinity, let's say this is the infinity, yeah, this point is a point at the infinity, the voltage will be 0. Yeah. Potential is a number associated with a space. What would be the use of this number? To show that, I'm bringing in another charge. Okay, this time, let's say 2 coulomb charge. 2 coulomb charge. Yeah. So I have this 2 coulomb charge. I'm going to place it at this point. Okay, I'm going to place it at this point. So now I have a 2 coulomb charge at a point where the potential is 10 volt. So you can calculate the potential energy U. Okay, use a different color. U. U is the potential energy, electric potential energy, just by multiplying these two numbers, 10 times 2. That is 20 joules. Okay. Now I'm going to move this 2 coulomb charge to this point now. Okay, this point here. So how do you calculate the potential energy at this point of this charge at this point? U equals potential at this point 8 times the charge 2, that is 16 joules. Okay, I'm going to move it again. 2 coulomb charge, I'm going to place it here. 2 coulomb charge here. Yeah. Now what will be the energy at this point? U equals 6 times 2. That is 12 volt. Sorry, 12 joules. Now I'm going to replace this 2 coulomb charge with a 5 coulomb charge. Okay. A 5 coulomb charge, another test charge. 5 coulomb charge. I'm going to place it here. Okay, I'm going to place it here. Now the potential energy will be 10 times 5, 50 joules. Place it here. The potential energy will be 8 times 5, 40 joules. Potential energy will be 6 times 5, 30 joules. You can see the potential energy is decreasing as we move away from the main charge, right? Or this positive charge has maximum potential energy when it is closer to the charge, to the main charge. So that's how you find the potential energy of electric potential energy of a test charge. All right. I have two oppositely charged plates here. So this is the one on the left is positively charged, the one on the right is negatively charged. So it will produce a uniform electric field pointing to the right. So that's the direction of my electric field. Electric field vector would be pointing from positive charge to a negative charge. That's why the direction is towards right. Yeah. So that's my electric field vector. Vector E. Direction of this vector is towards right, from positive charges to the negative charges. I'm going to bring in a positive charge. This is my positive test charge. I'm going to place it in between the two plates, let's say here. Because it's a positive charge, it would experience a force towards right. These negative charges here will try to pull it towards its side, and these positive charges here would push it towards the right. So it will experience a force towards right. This is the direction of the force. If you let it move freely, it would move towards right. It would accelerate towards right. But I'm going to move it against the electric field. I'm trying to move it towards left. Okay. So there is repulsion from the positive charge. There is attraction from the negative charge. But I am doing work. I'm trying to move it towards the positive charge. So I'm doing work on this charge, right? That work will be stored in this charge as its potential energy, electric potential energy. This is the equation for electric potential energy. Delta U equals minus work done on the charge. Delta U equals minus work done on the charge. So to increase the potential energy of the charge, of a positive charge, you have to move it towards the positive side or against the electric field. Now, if you want to decrease the potential energy, just let it go to just accelerate, right? This potential energy will get converted to kinetic energy. So it would move towards right, it would accelerate, the potential energy will be converted to kinetic energy. So when positive charge move towards negative charge, potential will decrease. When you try to move it towards the positive charge, you are doing some work, and this work would be stored in this positive charge as its potential energy. This is our equation, delta U equals minus work done, negative of the work done. Now, what is work done? What is work? What is work? What is the equation for work? Work equals force into displacement. If there is an angle between force and displacement, you should multiply with cos theta as well. So that's the equation for work done. And what is the force in our problem? F equals, we're talking about force on a charge, right? The equation is QE. We have studied the equation for electric field. Electric field equals force on a test charge divided by the test charge. If you cross multiply it, you'll get F equals QE. Yeah. So I'm going to replace force with QE. So that will give you work equals, replace F with QE. So QE d cos theta. QE d cos theta. That's the equation for work done. And delta U equals minus of work done, right? So what's the equation for delta U? Minus QED cosine theta. Minus QED cosine theta. Yeah. Using this equation, we are going to explain three different cases. So this is our equation for potential energy, change in potential energy, delta U. By the way, delta U is final potential energy minus initial potential energy. Let's say you're moving this positive charge. This charge was initially here, right? I'm moving it towards left. Okay, so this is the initial point. Potential energy at this point is ui. If you're moving it towards left, then this point the potential energy is uf. Yeah, the difference is uf minus ui is delta u. How can you calculate it? Negative of this charge q, electric field E, the distance you have moved, times the times cosine of the angle between electric field and displacement. Now let's have a look at the three special cases. Special cases. This is first case. Again, I have a positive charge here, positive discharge here. Yeah, and I'm going to move it towards the negatively charged plate. You don't have to do anything to move on its own, right? So the positive charge is moving towards right. Okay, so this is the direction of the displacement, towards right. Displacement is towards right. Electric field is towards right because on the left side we have positively charged plate, and on the right side we have negatively charged plate. Electric field vector will be from positive charge to negative charge, so direction of electric field is towards right, and the charge is also moving towards right. So let's find the change in potential energy, delta U. Now just define an equation, QED cosine theta. Alright, so delta U equals, sorry, there's a minus sign as well. So minus QED. What is theta in this case? Theta is the angle between electric field vector and the displacement vector. From the picture, it is clear that electric field vector and displacement vector, they have the same direction, right? So the angle between them is 0. They're in the same direction, right? This is E, this is D. The angle between them is 0. And cos 0 is what? Cos 0 is 1, plus 1. So the answer will be QED times 1. So delta U equals minus QED. Yeah, you have a negative sign, right? Means potential energy is decreasing. This is case number 1. Let's use some numbers. Okay, let's say we have this charge is I don't know, 2 coulomb, right? 2 coulomb charge, so Q equals 2 coulomb charge. Electric field is, let's say, 10 Newton per coulomb. E equals 10 Newton per coulomb. Displacement, the distance between this point and this point, let's say 1 meter. It's too long, but still, yeah. Okay, 1 meter. How will you find delta U? Delta U equals minus 2 times 10 times 1. That is minus 20 joules. So this positive charge would lose 20 joules if you allow it to move from this point to this point. Okay, that's the meaning of this equation. Okay, now the next case, the second case. This is case number 2. Yeah, again, we have a positive charge in the electric field. And this time, the charge is moving perpendicular to the electric field. This is the direction of the displacement, perpendicular. Okay, so in this case, electric field vector is towards right, and displacement vector is upwards. The angle between them is 90 degrees. So theta is 90 degrees, cos 90 is 0. Our equation for delta U is minus QED cosine theta. So delta U equals minus QED times cos theta is 0 because theta is 90, so times 0, so delta U equals 0. There is no change in potential energy. It will be the same. Yeah. Okay, now case number 3. In case 3, again we have a positive test charge in the electric field, and this time I'm doing some work and I'm trying to move it towards this positively charged plate. So this is the initial position. I'm moving it towards the positively charged plate. So this is the direction of my of the displacement of this positive charge. That's D. That's the direction of displacement. Okay, so electric field is towards right, and displacement is towards left. What's the angle between these two vectors? Yeah, what's this angle? This angle. This angle is 180 degrees. So theta equals 180 degrees. Cos theta equals minus, or cos theta, cos 180, sorry. Cos 180 equals minus 1. And the equation for delta U is minus QED cosine theta. So delta U equals minus QED. Cos 180 is minus 1. Minus 1. Minus and minus will be plus. So delta U equals QED. Yeah, that's the equation for potential difference. Again, let's use the same numbers. Q equals 2 coulombs. Electric field equals 10 Newton per coulomb. Distance 1 meter towards left. Okay, 1 meter towards left. So delta U equals 2 times 10 times 1, 20 joules. So if you move the positive charge towards the positively charged plate by a distance of 1 meter, you are increasing the potential energy of this charge by 20 joules.